Quantum networks, long seen as tools for secure communication, may soon help probe the link between quantum mechanics and gravity. A new study shows that entangled atomic clocks placed at different altitudes could detect tiny differences in time caused by gravity. This setup could reveal how quantum systems behave in curved space-time, offering a real-world test of quantum gravity using today's technology. Complete this video to know more about this topic. The study, published in PRX Quantum, outlines a new experimental protocol designed to test quantum behavior in the presence of gravity, specifically how time dilation caused by curved space-time influences entangled quantum systems. The core of the experiment involves using entangled atomic clocks, distributed across locations that experience different gravitational potentials. On Earth, this can be achieved by placing clocks at different elevations, where the effects of general relativity, though small, are measurable. Each clock's experience of time, while minutely different, should manifest in a quantum interference pattern if the clocks are placed in a superposition and allowed to evolve. What makes this approach feasible is its reliance on existing quantum technologies: precise atomic clocks, entanglement distribution via optical links, and quantum interference detection. By arranging the clocks in a W state, an entangled quantum configuration, the researchers can ensure that all nodes in the network contribute collectively to a measurement sensitive to time flow differences. The result is a method that doesn't require exotic conditions or theoretical constructs. Instead, it relies on controlled differences in gravitational potential and the fundamental precision of quantum systems to test a boundary where two great theories of physics, quantum mechanics and general relativity, might intersect. The study doesn't claim this will solve quantum gravity, but it provides the first realistic framework for measuring how gravity might influence quantum information. That alone makes it a significant development in experimental physics. Quantum mechanics and general relativity are both well established, yet fundamentally different. One deals with probabilities, entanglement, and uncertainty at the microscopic scale. The other describes how space and time are shaped by mass and energy. They work in their respective domains, but they're not mathematically compatible. For over a century, physicists have searched for a unified framework, a theory of quantum gravity that could describe both domains together. Many theoretical proposals exist, but experimental access to this overlap has been limited. Conditions where both theories matter, like near black holes or during the early universe, aren't accessible to direct study. This is why the new experiment is significant. It enables tests of quantum mechanics under conditions where gravitational curvature is present, even if weak. One key prediction of general relativity is that time passes more slowly in stronger gravitational fields. This time dilation has been confirmed with atomic clocks, satellites, and GPS systems. But until now, it wasn't clear how quantum systems in superposition respond to these subtle variations in time. If all predictions from quantum mechanics remain valid, even in curved spacetime, that's a valuable confirmation. But if unexpected phase shifts, coherence loss, or deviations from interference patterns occur, it might point toward new physical mechanisms. Some proposals, for example, suggest that gravity could play a role in collapsing quantum states, or that fluctuations in space-time could introduce non-unitary effects. The experiment uses Earth's well-understood gravity as a clean testbed. Instead of tracking particles in space, it measures how their internal states evolve. A powerful approach using atomic clocks' extreme sensitivity to test gravity's effect on quantum systems. What makes this work especially relevant is its practicality. Unlike many quantum gravity proposals that require unattainable energy scales or speculative particles, this protocol uses technologies available today: entanglement, clock synchronization, and coherent measurement tools. This allows not only lab-scale experimentation, but also room for scaling. For instance, placing clocks on drones, aircraft, or satellites could increase the time dilation differences, enhancing the signal-to-noise ratio of the effects. As space-based networks emerge, the infrastructure for such experiments will only improve. There are also secondary applications. If these systems are shown to respond measurably to gravitational differences, this could inform the design of ultra-sensitive gravitational sensors or next-generation positioning systems. These might be used in geophysics, space exploration, or anywhere precision timing and gravitational awareness intersect. The experiment also redefines what we expect from these networks. While they're often discussed as infrastructure for secure communications or distributed computing, this research demonstrates they can also be scientific instruments, capable of probing fundamental physics in ways classical systems cannot. It also lays a foundation for future tests. More complex configurations, involving larger numbers of entangled clocks, greater spatial separation, or entanglement with particles of different masses, could explore how different variables influence coherence in curved spacetime. These variants could either strengthen the case for mechanics' robustness or start to reveal patterns that diverge from standard predictions. The study explores whether gravity weakens entanglement. If superposition holds, it supports this theory's universality. If not, it could reveal new physics linking the quantum and classical worlds. While not solving this gravity, the experiment shows we can now test its edge, with real tools, not just theory. This research opens up a promising experimental frontier. Quantum networks aren't just for tech, they're now tools for probing the fabric of reality. By using entangled atomic clocks to test gravity's effect on these systems, we're entering a new era of discovery with the tech we already have. The frontier of this gravity isn't far away. It's ticking, entangled, and ready to be explored. See you soon!